Hi, I'm Lisa Weiland with the Wabash Valley Astronomical Society. This video is about reflector telescopes. We'll assume that you've already watched the telescope fair overview and accessories videos for prerequisite information and terminology that we'll be using.
When deciding whether to get a refractor or reflector telescope, remember that each type has advantages and disadvantages over the other. We'll be taking a close look at reflectors in this video and at refractors in a separate video. Reflector telescopes are cost-effective and they're particularly good for observing faint deep sky objects since they generally have larger apertures than beginner refractors. We recommend that buyers only acquire astronomical reflector telescopes with apertures of at least 114 millimeters, or 4.5 inches. Larger is better. In our telescope fair overview, we mentioned that reflector telescopes use a slightly curved mirror to focus incoming light. The way a typical reflector telescope works can be shown by looking at the path taken through it by incoming light. That'll be from the right end in this diagram. First, let's look at the principal components of a Newtonian reflector telescope without the tube itself being visible. Newtonian reflector telescopes are actually pretty simple in concept. They have three main optical components: the curved objective or primary mirror, which collects and shapes the incoming light beam, a small flat diagonal or secondary mirror, and an eyepiece to magnify the image. Let's follow the path of light as it passes through the telescope. Light from a distant object enters through the open front of the scope, shown to the right here, and travels the length of the optical tube until it reaches the objective mirror on the left side. The light is then reflected off that curved primary mirror into a narrowing cone until it reflects off a secondary mirror and then outward through a hole in the optical tube. Light comes to a focus just before reaching the eyepiece, forming an image. The eyepiece then magnifies the image before the compressed light enters the pupil of your eye. The colors that make up white light focus at slightly different distances when reflected by a spherically curved mirror. This can cause objects in an image to have false colored tinted edges called chromatic aberration if your scope has a spherical mirror. The chromatic aberration shown here for the Moon and Jupiter can be avoided by getting a reflector telescope with a parabolic mirror. These images were taken through cheap telescopes. Higher quality reflectors have a parabolically curved mirror, which focuses all colors of light at the same point. The distance between the primary or objective mirror, that's the one at the back of the scope, and the focal point is the telescope's focal length. The manufacturer usually provides the focal length as well as the primary mirror's diameter or aperture. Our accessories video describes how to determine the magnification or power when the telescope is used with a particular eyepiece. In addition to focal length, there's another number that's useful when determining your telescope's performance. It's called the focal ratio, or F number. This value is simply the telescope's focal length divided by the aperture size. It's usually represented as the letter F followed by a slash and then the number, as in F6 or F10. In this example, we have a telescope focal length of 900 millimeters and an aperture of 102 millimeters, giving a focal ratio of f8.8. If you absolutely must get a Newtonian telescope with a spherical primary mirror, try to get one with a focal ratio of f10 or higher to minimize chromatic aberration. As we've seen, a Newtonian reflector has two mirrors which need to be kept aligned with each other for best performance. Occasionally, you may need to make adjustments to keep this alignment. The procedure to do this is called collimation. The manual that comes with your telescope should describe this process. Collimation usually involves adjusting the secondary mirror at the front end of the scope and adjusting the primary mirror's tilt with knobs at the back of the scope. These collimation tools are sometimes included with your telescope package. The one on the left is a laser collimator. On the right is a Cheshire eyepiece, and the small one in the middle is a collimation cap. Directions for using them should be included with your package, whichever one of these, if any, comes with it. Although technically a catadioptric, sometimes low-cost Newtonian reflectors are sold with the Bird-Jones design. These have a spherical mirror and a simple correcting Barlow lens at the base of the focuser tube. We strongly suggest that reflectors having a Bird-Jones design be avoided due to the difficulty when collimating. A good way to tell if a telescope is a Bird-Jones is to compare the focal length to the actual physical length of the telescope tube. For example, suppose your telescope says it has a focal length of 1,000 millimeters, but then you measure the actual outside of the tube and it has a length of just 520 millimeters, about half of the stated focal length. This means there must be something inside to double the effective focal length, and that would be its little correcting Barlow lens. Better to keep Barlows in conjunction with your eyepiece. Then you can decide if you want to use one or not. One last note about reflectors. The image you see through a Newtonian reflector telescope is upside down. This is perfectly normal. In space, there is no such thing as up and down. If desired, you can get inverting diagonal attachments that will make the image right side up again. But I think you'll find it's really not necessary. Also, both mirrors in a reflector telescope are first surface mirrors. Unlike the mirrors you have in your house, where the reflective material is protected by glass over the top of it, first surface mirrors have their reflective material right on top of the glass. This means they cannot be cleaned with Windex and a paper towel. To do so will scratch and possibly remove the reflective material entirely, ruining your scope. If you get a reflector as a gift for a child, make sure to tell them never to touch the mirrors. These mirrors really have no need of being cleaned for several years, even if they get a bit of dust on them. If they ever do need a cleaning, they can either be sent back to the manufacturer or you can just contact your local astronomy club for assistance.
We've said that with aperture on reflectors, the bigger the better. And that's true to a point. But one final consideration is, can you lift it? For small reflectors like this one, I can easily lift both the base and the optical tube at once. That's why small reflectors like this are better for children, because they can pick them up by themselves. Larger telescopes, like this 8-inch, I have one just like it at home. Just the optical tube alone weighs 23.8 pounds. I can still lift that. Oops. And the base probably weighs about the same or close to it. On this scope, this is a truss tube Dobsonian. This is a design that you will find in many larger Dobsonians because they've tried to cut weight and shorten the length. All of this comes apart. The tubes are separate. You can take them off. You take off this front housing for the secondary mirror, and then you're left with the mirror well at the bottom. A friend gave me this telescope. I can't lift the mirror well by myself. I need help to do it. So that's one thing to consider. Consider the weight when you're choosing a reflector. A good reflector telescope can give a lifetime of enjoyment, observing many fascinating objects in the sky. If you have additional questions about telescopes or anything related to space and astronomy, please contact us through our website or by email.